Right, so if you remember in the last lecture, we dealt with the thorny subject of defectibility of complex functions. Complex functions, as you know, have the form u plus iv. U is a function of x and y, v is a function of x and y. So you put these two together and have the complex number I there, becomes a complex function. Now, unlike, like if you take a function in normal real space, like a function f of x equals to x squared minus y squared, that's a surface. If you remember from Maths 212, z equals to x squared minus y squared, or f of xy equals to z x squared minus y squared. That's a surface. You can imagine some surface above the coordinate plane in 3D space. So here we have a similar thing, except that we have two things going on here. There's a real part, u of xy, and there's a complex part, v of xy. So it's like two surfaces in the same problem. But unfortunately now we have gone beyond the realm of drawing stuff. This is a mathematical object from beyond this. In other words, I can't draw this. I can't draw surfaces. Unreal number I involved. I can't draw it. I call unreal for a reason. It's much like vector. Remember in vector analysis you came across when you were small, first year. Vectors were like arrows. At first, the arrows were in the two space, like an arrow on the XY plane. Then you grow up a bit, and then the arrows became in three space. You can have an arrow I plus J plus K. It's still an arrow, but in three-dimensional space. What happens in four-dimensional space? Suppose you have a vector A plus B, well, a vector with components A, B, C, D, like 1, 1, 1, 1. 1. How many ones did I say? 4 ones. How do you draw a vector of that type? 1, 1, 1, 1, 1. You can't draw it anymore, right? If you take a five-dimensional vector, you can't draw it. But it is a vector. And it generates a vector space. And all the stuff you learn about eigenvalues and eigenvectors, matrices and stuff, all apply to n-dimensional vector spaces. So the model of the tale is, we are past the drawing phase now, where you can draw a picture and say, this is what it looks like. You can't here. And, okay, you are quite within your rights to ask, like somebody did ask me in the last lecture, so how will this be useful then? Complex function. The way you're portraying it now as a useless function, can't draw it. Can it have any use? Well, as it happens in mathematics, you know, the mathematician tries to spin a tapestry. He's building a big object, a machine. Only at the end of the game, you look at it and you say, ah, that's the machine. That's what you were constructing all along. That's really what's happening here. We are building up the mathematical machinery, and slowly we are working our way to Cauchy's integral theorem, which is a marvelous theorem. In fact, it has another version on steroids called the residue theorem. And in that theorem, we'll be able to do integrations without actually doing integrations. And that theorem will help us to do integrals from minus infinity to plus infinity. You may think to yourself, what's hectic about that? And I know about this. In first year, we did improper integrals, where the limits were infinite. But those were carefully staged problems that you could handle at that level. The problems that you'll come across now are not of that type. They're much deeper. And they will be used to model realistic things like, I told you, in chapter 1 you had short rod, Laplace's equation in a square. It actually represents a square being heated some way, and you're trying to find the heat profile in that square. Now, in chapter 3, or 4 if you like, 4 chapters now, you'll come across the same problems, but this time the boundaries, it'll be infinite. The rod will no longer be a short rod from naught to L. It'll be from naught to infinity. Or you can even say minus infinity to plus infinity. And the Laplace square will no longer just be a square, it'll be a whole coordinate, whole plane, maybe the whole upper half plane. So then how does one do the integrations there? The ball game is quite difficult there, right? So now, what I'm building up to is that point. But always feel free, if you're not quite sure where we're going, always stop me and ask, because I should at least know where we're going. And sometimes you see it one lecture at a time, you don't see the bits and pieces, but it's building up to a certain point. So you need to hang in there a bit, all will become clear. But I must say, in the meantime, it's quite interesting mathematics. It's actually beautiful mathematics, if you ask me. Of course, you won't ask me. Now, let's today we're going to flood you with a few new words. So just hang in there, some unfamiliar words. Let's start off with the word holomorphic. Holomorphic. What does this word mean? Well, a function f of z, which is always in the shape u plus iv, is holomorphic at a point z naught if there is an open neighborhood containing z naught and u and v are continuous and satisfy the Cauchy-Riemann equations, the CRE. That is, they are differentiable. Remember, we showed in the last lecture that to show differentiability, we can demonstrate that the Cauchy-Riemann equations are satisfied. Cauchy-Riemann equations, ux equals to vy. In other words, day u, day x works out to day v, day y. When you calculate the two, you must get the same answers. That proves that the first Cauchy-Riemann equation is satisfied. And then vy equals to minus ux. That's the second Cauchy-Riemann equation. Both must be satisfied. And what's the other requirement that you must have for differentiability? Let's see if you were paying attention. Besides satisfying the Cauchy-Riemann equations, what else is necessary and sufficient to be differentiable? One more important thing, I said if you don't write it, you will not get full marks in the exam. Marks. Now you'll be thinking. As soon as you mention the M word, the people start thinking. You need to make sure the functions or the partial derivatives are continuous. The partial derivatives are continuous. But then it will be differentiable. So here we are saying that you have a point z naught in the coordinate plane, and this point is always surrounded by a neighborhood. So if it is differentiable at z naught, there will be a neighborhood around z naught wherein it will be differentiable. That's really what it is. It won't be an isolated point. Now, so basically for now, holomorphic means satisfies the CRE or differentiable. Those three words all mean the same thing now. Differentiable, holomorphic, satisfies the Cauchy-Riemann equations. There's one more word will come about later on. Non-holomorphic. Obviously, when you introduce a concept, one should then say what it is not. So non-holomorphic functions are f of z. I gave you two bad boys in the game. Which are the two functions that are not holomorphic? We dealt with them in class. Which two functions are clearly not holomorphic? They are not differentiable. Come on. What's that? 1 over z. Close, but not quite. There's two bad ones. You can try 1 over z yourself and check if the CRE works. I won't comment on that because you can check it out. One of them is bar z. That one is not differentiable. You remember? X minus iy. And mod z. That's not differentiable. You can quickly check the partially Riemann equations they figure it out. Remember, this is x minus iy. The ux is 1, vy is minus 1. Ux is not equal to 1 is plus 1, other is minus 1. Partially Riemann equations fail. So then, this is not holomorphic, it's not differentiable. Likewise, this guy here, the vy is 0, because it's a real value function. It's x squared, root of x squared plus y squared plus 0y. If you do vy, you get 0. Whereas if you do ux, you get some chain rule thing, they are not the same. So Cauchy Riemann equations fail. Now, another word, harmonic functions. Harmonic. This word you should know. Anyone know something about harmonic functions? Where have you heard this word before? What context? Have you seen it in other aspects of math? Or even physics? If you do physics, you will certainly come across harmonic. Harmonic comes from music, sound waves and stuff. When you think about what is the harmonic function there? Yep. Any ideas? Harmonic. Actually, we came across harmonic functions already, but we didn't mention the word. Harmonic functions satisfy Laplace's equation. Laplace's equation is del squared u equals to 0, or you can say uxx plus uyy equals to 0, or you can say day squared u dx squared plus day squared u dy squared is 0. Any function that satisfies Laplace's equation is a harmonic function. In particular, the sine and cosine functions are harmonic. Sound waves obey a sine omega t plus e. Sound waves are like the sinusoidal waves. Sound waves travel like that. They are sinusoidal. They obey a sine omega t or a sine omega x plus some number epsilon. So if you plonk a sine function in the Laplace equation, it will work. It will work. Now, okay, here we are dealing with two-dimensional functions. Let's just prove this. You see, from the CRE, you will recall that we have ux equals to vy and uy equals to minus vx. That's Cauchy Riemann equations. The small x means derivative with respect to x, partial. So for this one here, let me take day x. So I'll get uxx equals to vxy. Take the partial with respect to x on both sides. And for this guy here, let me take day y. Differentiate uy again, it'll be uyy. Differentiate this with respect to y, it'll be minus vxy. First, derivative with respect to x, and then with respect to y. Now, what happens when you add uxx plus uyy? You get vxy minus vxy, giving you 0. There you go. There you go. That's the Laplace equation. Uxx plus uyy equal to 0. Likewise, I can now get vxx plus vyy equal to 0. Functions that satisfy these equations, Laplace's equation, are called harmonic functions. They actually are a consequence of the holomorphic nature. They are consequences of the Cauchy Riemann equations, as you can see. So here's a small note, but I'll explain this note in more detail with an example as we go along. Just jot the note down, though. Note, if a real function satisfies Laplace, in other words, harmonic, then it is the real part of a holomorphic function, of some holomorphic function. Okay, so in other words, UXX plus Y is not. That's part of holomorphic. Means that U is harmonic and it makes up part of the holomorphic. B part can also be harmonic. So the entire holomorphic means satisfies the Riemann equations are Ux equals to Py, Uy equals to minus. Holomorphic means satisfies Riemann equations. Now, let's take an example. Any questions so far, guys? Basically, it's vocabulary here. Some words which I gave you the meanings of. So you've got to sit down and read these notes again to see that you understand the words. So let's take an example, u equals to x squared minus y squared. And firstly, we'll show it's harmonic, and then we'll find, yes? Then we'll find the accompanying function v, so that the whole thing is holomorphic. Okay? We'll find its partner. It's like conjugate pairs, in complex numbers. They don't exist by themselves. Two numbers exist as complex conjugates if they are solutions of some equation. Likewise, the harmonic functions appear in pairs, u and v. Both are harmonic. If they are, then the function is called holomorphic. Because then you know it satisfies the Cauchy-Riemann equations. Oh yes, one more thing, write f as f of z. Right, so firstly, we give you a starting point, some starting function u. You must firstly show that it's harmonic by hitting it with Laplace's equation, checking Laplace works. Then use that to resolve v. What is v? What's a partner? V. This is harmonic. What must the v be to also be harmonic? And lastly, can you write this entire function just as a function of z, not with u and v? Let's see how this works. I think it's not so difficult. So firstly, let's test the Laplace. U equals to x squared minus y squared. Let's take ux. What's ux? Differentiate that with respect to x. Treat the y as a constant. Ux will be? Come on, man. Come on. You guys need to participate. 2x. And how about uxx? Differentiate 2x now with respect to x. What? 2. Now let's take uy. This time, treat x as a constant. So you're dealing with minus y squared. What's the derivative of minus y squared? With respect to y, of course. Minus 2y. And what's the second derivative of that with respect to y again? differentiate this with respect to y. Yes? Minus 2. So we say clearly uxx plus uyy is 0. Minus 2 and plus 2 is 0. So u is harmonic. That settles the first business. U is harmonic. Yeah? That's the easy part. That's 1 mark in the exam. Yeah, this question can be quite long. Eh? It could be like about 4 pages long. And it can carry anywhere between 1 and 3 marks. Yeah, it takes a lot of work. So we have to reward you appropriately. No, it's not so long. It's probably about 5, 6 lines only. So let's find the. Let's start off with from the Cauchy-Riemann equations. From the Cauchy-Riemann equations, we know that ux is vy. In other words, vy is ux. And we also know that uy equals minus vx. So vx equals to minus uy. From the Cauchy-Riemann equations. So we are going to work backwards from this. So let's do the integration with respect to y. If you integrate with respect to y, you'll get v. And, oh, by the way, 2x, ux is actually 2x. And this idea, uy is minus 2y, so minus uy is 2y. You know what I'm doing? This 2x is in here. vy is ux, but ux we know is 2x. We know what is u. Our task is to find v. So we have made a connection between v and u. vy is ux. The connection comes from the Cauchy-Riemann equations. Likewise, the other Cauchy-Riemann equation tells us that vx is minus uy. We know what is uy is minus 2y. The minus of minus comes plus 2y. Now let's integrate both. One with respect to y, the other with respect to x. And then we'll see that it's easy to tell what v is going to do. Integrate 2x with respect to y. It'll be 2xy plus, I'm integrating with respect to y, so there'll be some function of x. You probably think it should be a constant. You would say if you integrate, you have something plus c. But remember, we have functions of 2 variables here. This is partial. There's x and y in the game. So when I differentiate with respect to y, all functions of x will become 0. There's no y. If you differentiate this guy with respect to y, it'll be 0. I mean, it could be a constant too. But why do we need to be so specific to say it's a constant? Its most general behavior is that it could be any function of x. So that's the first conclusion. On this side here, if you integrate with respect to x, you'll get v equals to 2y, integrate that with respect to x, it'll be 2xy. Plus, this time there will be a function of y involved. So let's say, what? G of y. If you integrate something like a number, if you integrate 5, it'll be 5x, 5y. So if you integrate 2y with respect to x, it'll be 2y x. You treat 2y as a constant. And then there will be some kind of a function of y. So that when so if you want to check that this is right, do the derivative. Differentiate with respect to x here. You take dx, you take y to be a constant. I mean, so you get 2y. Differentiate 2xy, so 2y will be that. Differentiate g of y with respect to x. You see, it works. You have to do it backwards. Now, let's compare these two guys. Both are expressions for v, if you notice. So they should be the same, right? Both are V. They should be the same. More or less, they are the same. 2xy here, 2xy there. That's good. But here we have a function of x, and here we have a function of y. What's the only way a function of x could equal to a function of y? This question I posed a long time ago in a different context. How is it possible for a function of x and a function of y? Yes. Provided both are constant, exactly. So this implies h of x equals to g of y equals to some constant. Let's call it c. So it turns out v is the function 2xy plus a constant c. That's the function v. If we test it, it will be holomorphic. You check it. Vxx plus vyy will give you 0, as you would expect. We're not going to test it because we did the same thing backwards, so it must work, of course, if we do it forwards. Now I've settled the second question. I found v. First, I proved u is harmonic. I used it to find v. Last question is to find f as a function of z. So the function f is u plus iv. And u is x squared minus y squared plus I. V is 2xy plus c. This part some students find very tricky. Get to z form. Remember, z is x plus iy. So to create a z, you have to massage this here to have things like x plus iy. Because whenever you see x plus iy, that is there. This part is a bit tricky. You will need to massage this to have x plus iy. This comes with a bit of experience and seeing it a few times. But I think let's firstly commence by doing the following. X squared plus 2xyi minus y squared plus ic. That's a bit of insight. Your insight will develop when you do a few of the tough problems. You do a few and then you learn how to connect different pieces together to form the set. So that's insight. That's like in your language you will say like, I wonder what that guy is smoking to realize that it works like that. But it's what we call insight and intuition. And with a little more wisdom, you may realize that that's actually x plus iy all squared. Just check it out in your head what it works. Square the first term is x squared. Multiply the 2 and double it, 2xyi. Yeah. Square the last term, I squared, if you square it, it's minus 1. It's minus 1, yeah. Y squared, y squared. So, but basically, you can see what I'm doing here. I'm running it backwards in my head. That's why I said it takes insight and experience, a bit of practice for you to see this. But then, now I've found that this is z squared plus ic. And that's what I want, f of z. It's now a function of z. There's no x, y, v, u, and stuff. Any questions, guys? The function to be differentiable, it must satisfy the Cauchy-Riemann equation. Then we said that when we came across the new word holomorphic, holomorphic means that there is a neighborhood around the point z0 within which functions can be holomorphic, meaning that they satisfy the Cauchy-Riemann equation. And then came across the word harmonic. turns out that functions satisfy Cauchy-Riemann equations, they're harmonic. You get uxx plus uyy is 0, yes? Example, if you were in school and you were asked to factorize x squared plus 4x plus 4, you would say, that's x plus 2 all squared. Because you learned it. You learned how to do this backwards. You learned that if you do x plus 2 into x plus 2, you get that answer there. So in time, you develop the ability to factorize this thing here. Or if I give you something else, if I say x squared plus 6x plus 9, how would you factorize that as a square? You would say x plus 3. That's because that's from your schoolwork. You learned that. Now we're doing the same thing, but we are doing it in the world of complex numbers. So your question is, I answered already by saying that you need some insights. Basically, you need to practice it and to realize that if you take something like x plus, okay, let's take x minus iy. And if I square it, it will be x squared minus 2xyi. And then square the last term will be I squared. I square this last term here. Like I'm squaring the term here, right? 2 squared is 4. Square this term, it will be I squared. What is I squared? Minus 1. So it will be minus y squared. So when you see this guy in future, your insights will be sharpened to know that, hey, I've seen that guy. It's actually x minus iy also. It's like factorizing it. But don't get too worried. You won't see weird ones in the exam or test. Who knows? Lecturers are never dirty and harsh. You always set the low-level, humble questions in the exam. So it's basically factorizing. But factorizing in complex numbers. That's the thing. Any other questions? Holomorphic means satisfies the Cauchy-Riemann equations. We have also learned that those functions will be analytic, U and V, meaning they satisfy the Laplace's equation. Did I say analytic? We haven't done that word yet. That's the next word, by the way. Let's carry on. Differentiable. Harmonic. I meant to say harmonic. We have done harmonic. There are so many words mean the same thing now, you see. So now we come across the word analytic functions. And don't get too worried. I'll preempt this. I'll tell you the story at the end, before we come to the end. It'll mean the same as holomorphic and differentiable. So don't get too worried. But let's give it its normal definition. Analytic means analytic. Basically, it means may be expressed as a power series. You can write a function as a power series. In other words, a Taylor series. And that's not surprising. You see that? All functions that are infinitely differentiable. Remember this result in first year? You must have been wowed by this result because this is such a spectacular result. Analytic functions. Well, you may not have used the word analytic, but Taylor's theorem came across. It tells you that all functions can be written as a series. Or, as long as you can differentiate an infinite number of times, because you need the nth derivative of f. So if you can't do the nth derivative, then of course it won't be different. There are no such simple examples you come across. No. Mathematicians do play around with some complicated ones with it. They don't satisfy the requirements. So you guys are all well behaved. So each of the x, sin x, cos x, tan x, sin x, cos x, sin x, tan x, cross. I hyperbolic sine log x, I can make a very horrendous ugly function and tell you to find the Taylor series. As long as you can differentiate it, you change the rule and normal tools, you can find the Taylor series. So then almost all functions can be expressed as Taylor series. So you can say they are analytic. In other words, you can write a function in our language now, complex language, f of z as the sum of some coefficient z minus a to the power k. I shouldn't use a there, but anyway, k equals to 0 to infinity. So that it can be like a0 plus a1 z minus a plus a2 z minus a squared plus blah 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 up to infinity. That's the Taylor series. An example is the geometric series. This is the one you came across in school. F of z equals to 1 plus z squared plus z cubed plus blah blah blah. And provided mod z is less than 1, provided the ratio is less than 1, what will be the sum to infinity of that? How do you work out the sum to infinity from high school? Sum to infinity. Huh? What's the formula for the sum to infinity of a geometric sequence? Series. Isn't it a over 1 minus r? A is the first term, the ratio is z here. So 1 over 1 minus z. So the expression of 1 over 1 minus z can be written out as Taylor series like that. Think of it backwards. And that's how you also find the integral of limbs 1 plus z and 1 minus z and stuff. I mean, you did that in first year. I'm not going to do that again. You may write this as z to the k equals to 0 to infinity. The coefficients there are all 1. They need not be for other sequences. So other famous ones are e to the z, sine z, cos z, sinh z, cosh z, cosh, lim, sine z. See, I can build up any kind of fictitious function, but you can actually check it's going to be, it'll have a Taylor series expansion. As long as you can differentiate it. At this complicated block here, you can actually use it. The derivative of cosh is sine, then you multiply with the inner function. The inner function has another inner function, and so on and so on. Can be done. Oh, by the way, how do you expand e to the z? Isn't it sigma z to the k over k factorial? K equals to 0 to infinity. So it's 1 plus z to the 1 over 1 factorial plus z squared over 2 factorial plus z cubed over 3 factorial and so on and so on. Likewise, I can do sine, which is x minus x cubed over 3 factorial plus x. Let me write a few. Sine z is z minus z cubed over 3 factorial plus z to the 5 over 5 factorial minus z to the 7 over 7 factorial, blah, 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 blah. Cos z. If I can't remember cos z, I can get the answer from sine z. How do you think so? Think of a way to get the answer from this. Suppose you can't remember the expansion of cos z. I can differentiate sine z. What's the derivative of sine z? Cos z. If I do this, the derivative will be the cos z answer. So differentiate z is 1 minus 3z squared over 3 factorial. The 3's will cancel. it'll become z squared over 2 factorial. 5z to the 4 over 4 factorial. 5z to the 4. The 5 will kill the first 5 in 5 factorial. So it'll boil down to z to the 4 over 4 factorial. Minus, likewise, z to the 6 over 6 factorial, and so on. That's how you do sine and cosine expansions. Any questions? Is it coming back to you from first year? See, in first year, you also were thinking the same thing. I wonder where this is useful. Can this thing have a use in the first place? I don't know why we're learning all this stuff. It's just to pass some exam. Are these guys just torturing us with some very complicated stuff and just to see if we can jump over some hoops and hurdles? No, it's all part of a bigger picture. These things are part of the big game of mathematics. And I can assure you, humanity wouldn't go any distance forward if we didn't do the heavy lifting in mathematics. Science would stall completely if the underlying engine didn't run. So you can only do so much with experiments like trying out a rocket to see if it reaches the moon and stuff. But mathematicians can sit in a room, do pen and paper calculations, and decide if a rocket will reach the moon or not. Physicists and engineers will build many rockets. Let's build 50 rockets and try them out. The first one misses by 10 kilometers. Let's change the mass of this thing now and see if it hits the moon. It didn't work. Let's do something else. Yes. Hmm. Yeah. 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 In other words, we'll still be able to find these Taylor series. As I invented that silly one, cos, sine, then z, and stuff. You can make up this crazy ones if you like. As long as you can differentiate infinitely, the game is on. Any other questions? Have you got a question or are you yawning? You're yawning. Okay, now what was the thing? Analytic. Yeah, let's now talk about some properties. Properties of analytic functions. So you can just write this down. If f of z is analytic at z naught, means that you can expand it as a Taylor series, right? Then there exists, this symbol means there exists an open circle centered at z naught, such that every point, open circle C, let's say, every point in C is analytic. And of course, differentiable. So one conclusion we can gather from this is that the function is holomorphic. Holomorphic if it is analytic at z naught. That's what I was saying earlier on. Holomorphic, analytic, differentiable mean the same thing. Holomorphic means satisfies the Cauchy-Riemann equations. Then the additional fact we learned was that such functions, each part, the real and imaginary parts, are harmonic. We learned that as an additional fact. And something else. This analyticity implies term by term differentiation can be done. These are the consequences of analytic behavior, because you've got individual terms now, you see. You've got a sequence of independent terms. You can differentiate them one at a time. The derivative of a sum is the sum of the derivatives. Derivative of f plus g is a derivative of f plus the derivative of g. It's a famous, well-known result. It's like an obvious thing. So, as I was saying, words like holomorphic, analytic, differentiable, they are similar. They mean the same thing. And in all cases, we can say that they satisfy Cauchy-Riemann equations. The central thing that binds them. What are the Cauchy-Riemann equations? Ux equals Vy, Uy equals minus. What comes next? You want a short break? Oh, well, let me just do this, two examples, then we have a short break, right? Let's just go past halfway. Let's do this. Break into integration. So I just want to give one or two examples of this term-by-term differentiation. Let's take an example of e to the z. We know it's sigma z to the k over k factorial, k equals to 0 to infinity. If you want to expand it, it'll be 1 plus z squared over 2 factorial plus blah, 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 blah. If I take the first derivative, d dz, I differentiate first, I will get derivative of e to the z, which is e to the z. Differentiate z to the k. See, I can differentiate it here inside the sigma. It'll be kz to the k minus 1. Like a normal derivative, because I can do it term by term. So this will be sigma kz to the k minus 1 over k factorial. K equals to 0 to infinity. And do a little massaging here. This will be sigma kz to k minus 1. Remember this here, k factorial is the same as k times k minus 1 factorial. I can kill the k's. And this can boil down to exactly the same shape. Z to the k minus 1 over k minus 1 factorial. K equals to 0 to infinity. It has the same shape. Because you know, the derivative of e to the z is e to the z. If I differentiate these guys, I get 1 plus 2z over 2 factorial, which is z again. Plus, then you get the same z squared over 2 factorial. It will be the same thing again. That's a remarkable thing about e to the z, or e to the x. It's indestructible. You differentiate it infinitely, it remains the same. And if you do the second derivative, d squared dz squared, again this will be e to the z. Here you can say, so differentiate this guy here, it'll be sigma k minus 1 z to the k minus 2 over k minus 1 factorial. And you can see that k minus 1 factorial is k minus 1 into k minus 2 factorial. So it becomes sigma z to the k minus 2 over k minus 2 factorial. It has the same shape, etc. let's take sine z. We said that that's z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus z to the 7 over 7 factorial, etc. If you differentiate this d dz, you get cos z here, and that's 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus blah, 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 blah. If I differentiate it one more time, d dz, d squared dz squared, derivative of cos z is minus sine z. I wonder if it'll come back to the original one. It'll come back to this guy. Shoot, well, the negative of it. So differentiate this is 0. Here you have 2z to the 1 over 2 factorial. 2's will cancel off, so you'll get minus z. This one here will be 4z cubed over 4 factorial, so it will become plus z cubed over 3 factorial minus z to the 5 over 5 factorial, etc. It's exactly the same as the first line. Remember, there's a minus sign here. That minus z, that becomes plus, minus, so on. The same thing. That's what we mean by term differentiation. Okay, let's pause here at this stage.